Hello everyone. I hope you're all enjoying this fundamental materials on bioenergy, biomass energy. Today I want to go through some problem examples that would touch briefly on a question in thermodynamics, which is the model you've just covered, and then we'll try and link this to a biochemical problem, which is related to what you'll be covering in this module, and hopefully you'll find these examples very informative. I have a simple question here, a kind of straightforward question, which tells us to calculate the heat of reaction and the change of enthalpy for biogas containing 60% methane and 40% CO2 that was combusted in a gas turbine, and exiting the system at 1000 Kelvin. The question tells us molar basis, and this is pretty very straightforward, one of the easier ways to calculate, which means for every 0.6 mole of methane we have 0.4 mole. Another variation to this question would be on a mass basis, and whatever reference compound that's given, you find the percentage of that reference compound, and then you convert the mass to moles by dividing it by dividing the kilogram by the molar mass of the substance. Anyway, this question tells us specifically that we have 1 kilomole of methane, so we'll use this 1 kilomole in our stoichiometry, and if we use that, we'll be getting 60% of that 40% of that biogas with 1 kilomole of methane will be 0.67 moles of carbon dioxide. So the first question, heat of reaction, we have this formula in Brown's book, and we talked about that in last module. So when you use this formula, we have the enthalpy of formation times the number of moles of the products, and then subtract that of the reactants, and you get your heat of reaction. So I've just produced Brown's table here, and this is our equation. So this is our product. So you come to this table: CO2, carbon dioxide, this is your value, and then water, which is as a vapor here because this combustion. Water is a product, as a product is vapor. And our reactants, we have methane, CO2, oxygen, and we have methane, CO2, and we have oxygen. So you put this in your equation, you get your answer. It looks quite easy, doesn't it? Anyway, let's move on. So we change in enthalpy. Calculating the change in enthalpy, we have this formula to which we'll find the differences in the enthalpy at the different temperature. T2 minus the reference temperature, which is usually taken as the temperature standard conditions, and then we have T1. Where's my cursor? We have T1. This is the temperature at which the compounds are entering to the turbine. This is our reference temperature. T2 is the temperature at which it is exiting, and this is our heat of reaction, which we've calculated already. So in the same way, we'll look up the table. This time a different aspect of the table. We're not looking at the enthalpy of formation, we're looking at the molar enthalpies at different temperatures. Our T2, this is our T2, this is our T0. We know T1 is equal to T0, and that's because we're told that the temperature is getting into the biogas is getting to the turbine at 298. I will talk a little bit about this later on. So we take these values, we set them in this equation. That's what we have as our new equation, and then we get our answer. Again, looks pretty much straightforward. You have to be careful with your signs. And then here I'm just looking at the assumption we made earlier on that T1 is T2. I'm just trying to give you a graphical depiction of what's going on. And T0 is usually a reference temperature, and like I said, it's that reference temperature is the standard temperature, which is 298 Kelvin. And the question we have says the biogas is entering the system, the turbine, at 298. So in fact, that's not an assumption. It actually makes us aware that T1 is equal to T2, and that's what we're seeing here. T1 and T0. Sorry, I said T2. T1 is equal to T0, and this is our exit temperature. I have some two other graphs here which are not related to the problem we're solving here, but I think it will be nice, it will be interesting to just study them and understand. We've talked about adiabatic condition in our last module, and we see that we say our change in enthalpy is 0, and I'm just giving the graphical depiction of what it is, and that's partly because, again, T1 and T0 are the same, so we have the 0. So our change in enthalpy, heat of reaction, is also equal to the molar, sorry, there should be a negative sign, the difference in the molar enthalpies. So let's have a little variation to this question. Suppose biomass has 100% relative humidity, or sometimes they use relative saturation. What does that mean? So you can read this text, you can pause this video and read, or you can read from the website, the course material on the website. I just decided to give a little brief recap. We'll deal with this later in I think 2 or 3 modules from now. So a little bit about biogas to give us an idea, some components in it. And what I have here is that raw biogas typically has a relative humidity of 100%, and this means that it's transporting as much moisture as it can hold at that given condition. And so I want us to look at stoichiometrically and bioenergetically, and show that reason why we have water in this biogas. So this is a simple example. We're producing biogas from glucose, and this is our glucose. These are half reactions. By now you're getting familiar with the concept of half reactions. We have a half reaction for glucose and a half reaction for methane. Notice that when you change from table 2.3, when you change the position of the products and reactants, if you interchange the product and reactants, your sign, your free energy sign changes too. So if these things were initially in the table were on the left hand side, and you now brought them to the right hand side, and this was a 41, it will now become a negative 41. And then when we have the half reactions, we just add them up, and this is just as it is, adding up. If we have a singular product, if this product is not at this side, it remains at that side. If this product is at this side, it remains at this side. And then the other ones like water, I can shift water from here. Once it crosses the reaction sign and showing the product, the sign showing the product, the sign serve as an equal sign. The sign would change. So if I move water in my dish, if I move water to the side and then I do my subtraction, the sign would change. If I do my subtraction and my answer is negative, it would mean water is supposed to be at the other side of the equation. And if it's positive, then it remains at the place you've moved it to. So you don't have to mind, you can move it anywhere to do your subtraction. The sign will tell you where the actual place should be. And then we'll have our hydrogen. If you move it across, since they're the opposite side of the equation, they would cancel out, because if you move it, the sign would change. That will be positive minus negative H, and that will be 0. The same with the electrons. So in bioenergetics, we're learning that we don't just have energy equation, we have the synthesis equation, because the microorganisms we're using to perform our reactions, they need energy. The reason why they are interested in the substrate we're giving them is because they want to extract energy from it. They want to grow, they want to maintain themselves. So part of that substrate is used to build up the microorganism and produce more cells. So that substrate is glucose here. They'll have a microorganism that would need nitrogen source. In this case is ammonia carbonate, and we have the cells. This is a formula for microbial cells. So we have a cell produced in water. We'll combine our synthesis reaction, and we'll have this. And then when we combine the energy reaction, that's what we did the very first set. And then we combine our synthesis reaction. That's the reaction. Total combined reaction of our reaction would have. And here you see that methane, the water from the microbial metabolism, and CO2 are collected in the headspace. And you can read this note. So the essence of that digression, of course I should have told you earlier when we were digressing, the essence of that digression was just to show that normally water is produced in biogas. Water is part of the product we get from that reaction, and water can be collected in the headspace of our tank, our drums, or whatever system we're using. And water can also be produced from vaporization, depending on the temperature of your system. Vaporization of the liquid in the substrate. So our question says biogas have 100% relative humidity. It means it's holding the maximum water it can hold. Is this unusual for biogas to contain moisture? No, it's not unusual. It's very, very common. And usually this water would have to be, the biogas is usually cooled down and the water is condensed out, and sometimes other mechanisms are used to dry. Now, but when we look at this equation, we would find out that the ratio is not exactly the same as the ratio we have in our question. But usually some of the CO2 dissolves in the water that's in the substrate left in the tank, so that the one in the headspace, collected in headspace, is usually lower, and that increases amount of methane. But here I want us to, I've just quickly calculated based on this stoichiometry, we'll find out that we have 28.8 kg of water. But the question is that, is this the amount of water collected together with the biogas? The answer is no. We have to look at the condition to be able to know whether all of this water can be held, because the biogas at a given temperature will have a certain water holding capacity. So if a lot of water is there, it doesn't mean the biogas can hold it. Some of this water may condense back into the system. So to find this, would use our psychometric chart. We don't have one in this course, but this just because we're looking at practical aspects of things, I just thought this example would be good. Okay, use a psychometric chart to determine the water holding capacity. The assumption I'm making here is that biogas behave similarly to air, and the good thing is that we have two properties we can use: the dry bulb temperature and the relative humidity. So once we have two temperature, we can use this chart to find a third property, not just a third property, many other properties once two properties are known. But now we're just interested in one property, that's the moisture that can be contained biogas at this temperature and this relative humidity. And we'll look at it. We'll find that it's holding 0.2. Now we'll look here. These lines, these curved lines, are the lines of relative humidity. So at this same temperature, we discover that if the relative humidity is lower, that the moisture in the water will be lower. And if the temperature is higher, we'll find the moisture in the biogas will be higher. Anyway, from this chart we would find out that 0.2, which is this 0.002, it's not very clear. Water is in a kg of biogas were implied, and so we have in our equation is 1 kilomole of biogas, which contains 1 mole of methane and 0.67 moles of CO2. Our mass is 45.48 kg. So using this mass, the amount of water that will be held will just be very little. So you can imagine we calculated 28 point something kg of water, but only less than 1 kg of water is in the biomass. We can translate this to the number of moles and then use that in our stoichiometry. And then, just like before, and I'm sure we should be familiar with this very well, we just look for values, heat of formation, and then we know our number of moles, set it, and we'll find our heat of reaction. We see this value is not different from what we calculated earlier on, even though we have water introduced here. It's still the same, and the question is why. I will leave that for you to answer. So we'll move on. Changing enthalpy of the gas stream. Now we have water in our biogas. Is the change in enthalpy going to be the same? Now when we calculate the change in enthalpy, we discover that the enthalpy value is changed. It's lower. So again, the question is why? Why is the difference in the enthalpy? No difference in the heat of reaction, but difference in the enthalpy. So you think about that. Now another variation. Suppose biogas is at 35 degrees centigrade, and that's very likely because biogas is usually most biodigestion systems would be operating around this temperature. But most of the gas will be usually at ambient temperature because, like I said, water is contained in it and it has to be cooled down to condense that water. Most of those waters are condensed through cooling. In some cases, some other additional methods are used to dry the air, but most times just condensing the gas. But assuming the gas is not cooled and straight from your biogas you take it to utilize, and we assume it's at 5 degrees centigrade. What happens this time? Yeah, one thing we know is that T1, oh, that's a mistake. T1 minus, this should be negative. T0 is not going to be 0 this time. Why? Because our T1 is not at our reference temperature anymore. So if you recall the chart I was showing, we had 3 charts there. So you see the chart to the right of those 3 charts will be depicting our new condition where T1 is different from T0. Well, that's the same chart Brown has in his textbook. Now the thing is that we don't have enthalpy values for 35 degrees, which 308. So what do? You can plot an HT value using the table values in table HT graph, using the values in table 2.1. That's this. Plot this for each of the compounds. This example, this against this. And you can now add a trend line, and then you show the equation. If you use Excel, you click show equation, and you have an equation showing the relationship between enthalpy and temperature. So you can now put in your temperature value and get the enthalpy value, which is going to be somewhere between these two. So that's a check. The value should be between these two. Okay. And then the other problem is that we don't have methane here. Now we're saying that T1, the reaction cannot be 0. The reactants portion, it cannot be 0, and we have methane as a reactant. So we need that. We don't have it in Brown's text, but you can find that on the internet or in other texts. I don't have one readily in my mind now. So that's it. Now the other thing is that at 100% at 35 degrees C and 100% relative humidity, the moisture we calculated is not going to be the same. Like I showed you earlier, higher temperature, the carrying capacity, water carrying capacity is higher for gases. So the moisture in the biogas will be higher than what we calculated earlier. So you need to factor that in, calculate the new moisture, and then you follow the same procedure to calculate your heat of reactions, and your heat of reaction, you're changing enthalpy. Now let's look at an example of biochemical process. Biochemical would involve microorganisms, and we'll see how it's different from the thermochemical process we looked at earlier, or is the combustion of biogas. Here again, we look at half reactions to form our overall reaction. There's the energy reaction, and we have our corresponding Gibbs free energy. Again, like I told you, you have your half reaction, you just add them up. You bring water to this side. If you subtract and it's negative, it means it should be on the other side. So in this case, if you move water here, it will be negative, so it will be on the side. And we have only one CO2, it comes down. Now methane. Like I said, when if the half reaction, if the position has been changed, you change the sign on your Gibbs free energy. Otherwise, instead of adding, you have to subtract it. So in this case, because we've already changed our sign, we'll just add energies, and then we'll have 0.102.24 per electroequivalent. An electroequivalent, we're referring to the energy per any electron donated, okay, and or electron used. That's per electron equivalent. So for our overall equation here, energy equation, we'll find out that we have 102.25 kilojoules per electron equivalent, but that is for 1/8 methane. So for 1 mole of methane, the energy will be 8 times what we've calculated here. So times 8, and we're having 818 approximately kilojoules per mole. This value is different from what we calculated, our heat of reaction calculated under thermochemical oxidation. I want to draw our attention to something. Even though the value is important, we pay attention to the sign, and I want you to think about it. Why do we pay attention to the sign? And then the other question is, why are these two energy values different? So for one, this equation, we aren't using the same equation. The original equation we looked at in problem 1 has carbon dioxide, because we're not just, biogas is not just methane, it has carbon dioxide, but our reaction here just looks at methane. So if we have this exact equation and someone tells you that it's a biochemical reaction, will you expect the energy to be different? So that's what we're going to look at now and see. So in calculating the energy, we use the Gibbs free energy table in Appendix A of Ridhma and McCarthy, and then similar to how we calculated the heat of reaction, we sum up the various compounds that form our products, and then the Gibbs free energy and the number of moles of each of those compounds, and then we subtract the reactants from that. So I didn't show the table here, but when you look at that appendix, you'll find these values, and then you'll notice that water in this case is liquid. We're seeing water as liquid. Some of it will be vaporized, definitely, but we're assuming it's liquid. And we see our Gibbs free energy gives us 338, but assuming water is gas in this equation, and again at 35, if we're assuming 35 degrees, it's likely we'll have a lot of water as gas. Assuming water is gas, what would the energy be? Because in our thermochemical reaction we say water was gas. We don't have the formula for gas in the appendix A, but you can check that on the internet and you get this value. If we use that value instead of 237, which we used, we see our energy system will be 816, which is still higher than what we calculated in the thermochemical equation example. So the question is that if we have 816 and 802, what happened to the difference? How do we account for this? Where has this gone to? The 14,509 kilojoules of energy. Or perhaps we should be asking, is that the right way to compare these two things? Most times in the biochemical reaction we're looking at the Gibbs free energy, and when we're looking at the thermochemical reaction we're looking at the enthalpy. So the thing is that these two equal. No, they are not. We have the relationship here. Here I have a relationship that shows the Gibbs free energy is equal to the enthalpy minus the temperature and the change in entropy. So from what we have now, our 816 is our Gibbs free energy, 802, which is the heat of reaction. We'll find out that the 14,509 would then be this term, which is also an energy term, but this energy is, I like to call it like lost energy, energy due to the disorder of the system, which the disorder is necessary anyway to allow the reaction proceed. The higher the disorder, the more spontaneous the reaction will be, or the easier for this reaction to proceed. So part of this energy goes into the entropy. So the Gibbs free energy is the available energy, or the change in the Gibbs free energy is the change in energy that is available to do work, while the enthalpy, change in enthalpy, or the heat, which represent the heat of reaction in this case, is the energy released, or the non-mechanical work done. So in combustion systems, we want to know the energy released, and so that's why we focus on the enthalpy. And Gibbs in thermochemical biochemical reactions, we want to know the energy that is available for the microorganism, part of which will be used for its metabolism, and what will be left in our system. I'm going to stop here. It's quite a long example, so I'll stop here. If you have any question, like I said, I wanted to just be brief, point out some things quickly. You have this on the website. If you have any question, you can channel them to the discussion forum. If you have any addition, you can channel it to the discussion forum. Yeah, let me know your thoughts on all this, and I hope you enjoyed the rest of this module, and just keep enjoying the course. Take care. Bye bye.